take a seat if they can, please. It's fantastic to have the problem of so many people. So welcome to those obviously in the room. We've also got people online. Welcome to the physics department here at Imperial and to the inaugural lecture of Professor Mitesh Patel. So these lectures give us the chance to celebrate the work of some of our new professors. So as Mitesh is a particle physicist, it's my pleasure as the head of the particle physics community here at Imperial to get the pleasure of introducing this evening's events. So let me just say a few words and then it'll be across to the speaker very quickly. So in terms of housekeeping, we are not expecting any fire alarms. So if a fire alarm does go off, please orderly exit via the fire exits to the gathering point, which is on the corner of Prince Consort Road and Exhibition Road. We will have an opportunity for questions at the end, both people in the room and online, and obviously the event is being recorded. So enough of those announcements. Turning to the subject material, particle physics, as those who have read the abstract will already know, study of the fundamental building blocks of the universe and the forces that govern them, fundamental stuff, elucidating the origin of the universe, back to basics in that sense. We know, well, our current picture of the standard of particle physics is what we call the standard model. That's built on symmetries. Folks, come down. There's plenty of space down at the front. We've got whole rows down the front. Symmetries and conserved quantities. You're going to make me keep talking as people come in. Anyway, that's what it's based on. We know it's been fantastically successful, but it's incomplete. Now, there are two ways you can look for physics beyond the standard model. This is where Mitesh and I actually start to diverge. You can either produce that new physics directly, but then you're limited by the energy of your collider, or you can look at rare decays and look for the effect of that new physics on those rare decays. And then you're not limited by the energy of the collider. Really, you can do anything you want up to whatever level you want. And Mitesh has been a pioneer of this approach with the LHC's flagship experiment in this area, LHCb. Come down, folks, come down. Plenty of space. We've got a whole row at the front that's not being used. Let me pause just while people come in. So in fact, some of the most interesting measurements in particle physics, the most exciting over the last few years, have been in this area, pioneered by Mitesh and his team, and that's what we're going to hear about as we go on with his talk. Just a couple of other things, if I may, about Mitesh before we start. That's the research, that's what we'll hear about, but there's so much more in terms of what he's done for the group, or as I should say now, the community, taking on various roles, both the community here and the particle physics community as a whole. He's the chair of the Particle Physics Grants Panel, the primary review body in our area, so that's a big effort, and we're looking forward to the outcome, we hope, which is coming soon. And also, he's a passionate advocator and teacher and educator, I think typified by his recent award of a college teaching award just last year, or the year before, in fact. On a more personal level, I'm delighted to say I had a small part to play in actually his arrival at Imperial, and it's been absolutely fantastic to see how he's grown, flourished, fantastic guy to work with, and now, of course, Professor. So over to you, Mitesh.
Thanks very much. Okay, so maybe I can try and unpack this title a little bit. I've spent the kind of 20 years of my career thus far measuring a bunch of different processes. These are called loop processes. And I'm going to, over the course of the next first 40 minutes, try and explain why we're interested in these particular processes. So give you some background, some context to these studies. And then I'll try and explain what we see in our experiments. And we'll see a picture emerge from that isn't yet very clear. So I'm going to wind up by trying to ask a question about how we might get some clarity about what we're seeing. So let's get started. As Professor Davies said, particle physics is about the study of the fundamental constituents of matter, what things are made of at the most basic level, and the forces that act between that matter. And perhaps that makes some people think about the atoms that they were taught about at school. So if we take the example of a helium atom, then we have an understanding that this is composed of a dense central nucleus that comprises most of the mass, and this is made of positively charged protons and neutral neutrons. And then somewhere flying around the outside, we have negatively charged electrons. A series of experiments smashing the constituents of atoms together during the 1960s taught us that actually this picture isn't complete. These protons and neutrons in the nucleus, they're not fundamental. They have substructure. And we now understand that in fact they're made of these particles that we call quarks. So a proton is 2 up quarks and a down quark, and a neutron is an up quark and 2 down quarks. And heavier versions of these quarks exist, and there are also heavier versions of the electrons that make up matter. We also have an understanding of how the fundamental forces work. We understand now that the forces are conveyed by the exchange of some additional particle. So it's a bit like the exchange of a basketball between 2 players. There's something that passes between them that conveys the action of the force. We know of 4 fundamental forces. Perhaps the one that will be most familiar to everybody here is the force of gravity. So the force that keeps the Earth in orbit around the Sun. But the strength of gravity depends on the masses involved. And in particle physics experiments, the masses are absolutely tiny. And so actually gravity has no impact on our experiments. We can't see its effects. And then perhaps you're also familiar with the force of electromagnetism. This is the force that keeps those electrons in orbit around that positively charged nucleus. It's conveyed by the exchange of particles we call photons, the particles of light. Then perhaps less familiar to some of this audience is the weak nuclear interaction. This is really important in processes that happen in the sun, so to help convert hydrogen into helium, the burning of the sun that happens. So the weak interaction is critical for that, and it also is critical to radioactive processes, some of the radioactive processes. It's conveyed by the exchange of particles we call the W and the Z. Now those particles turn out to be rather heavy, and so this force is rather short range. And then finally, the 4th fundamental force we know about is the strong nuclear interaction. This is conveyed by particles we call gluons. And those gluons self-interact, and that gives the strong interaction rather unique properties compared to the other forces. One of the downsides of that is that it makes it, with our current methods, very difficult to compute the effects of that force very precisely. And that's something we're going to come back to. Okay, so that brings us to this picture, which represents the so-called standard model of particle physics. So we have on the left here the matter particles. Here's the up and down quark that make up the protons and the neutrons. Then we have the electron, that's the other element of ordinary atoms. And then down here we have an additional particle which really doesn't interact with other particles very much. So it doesn't like to talk to the other particles. It's neutral, we call it the neutrino. On the right-hand side here, then we have the force-carrying particles. Here's the gluon of the strong interaction, the photon that conveys the electromagnetic interaction, and then the W and Z particles that convey the weak nuclear interaction. And then the Higgs is the particle that we think that gives all these fundamental particles their masses. What's surprising, and we don't really understand at all the reason for, is there turns out to be copies of these families of matter that we see. So there's a heavier version of the up quark that we call charm, a heavier version of the down quark we call strange, a heavier analogue of the electron we call the muon, and another neutrino. And then this pattern repeats. There's in fact a third whole family of matter particles. Top, the bottom or beauty quark, the tau lepton, and then another neutrino down here. And we really don't understand why there is this repeated structure, why we have multiple versions of these different families of particles. So it's perhaps tempting to think of this as the particle physics equivalent of chemistry's periodic table, which you see pictured on the left here. But I think it's worth emphasizing that this is much more than just a classification system. This is a mathematical, quantitative theory from which we can determine the processes that are allowed and everything about the way the particles interact with each other, taking only a few input numbers from experiments and having an understanding of the so-called symmetries that apply. And it turns out that these symmetries have a central role. So imagine we want to understand the motion of this plane as it loops the loop. The laws of physics that describe this shouldn't depend on whether I measure the motion of this plane from this coordinate system over here, or if instead I observe the same situation looking from over here. In the jargon, we say there's a symmetry of the system. If we move the coordinate system from one position to another, the physics shouldn't change. And that allows us to constrain the kinds of pieces that can appear in the equations that describe the system. So the symmetries that apply in quantum physics, they're a bit more abstract. But the principle's the same. The symmetries that apply dictate what can happen. They help us really have a prescription to write down the laws of physics that we think should apply in this system, even new laws that we might not yet know about. Now that's so much the case that some of my colleagues spend their time turning this round. They ask the question, if the symmetries of the system were this, what would the physics be? What would I observe in experiments? And can I predict, in addition to the phenomena we see in current experiments, can I predict new phenomena, which, if someone measures that they really turn out to be the case, would tell me my guess about the symmetries is really right. So symmetries is really central to this kind of physics. And the Standard Model is an incredibly successful theory. It's predicted the results of essentially all experiments basically since the 60s. It's really incredibly precise. One can get really a very good idea of how the particles interact. So imagine we want to understand how an electron behaves in a magnetic field. That's related to this quantity that's known as the anomalous magnetic moment, and we can predict this in the Standard Model. So predicting it in the Standard Model requires adding up lots and lots of these complicated loop processes, and we can do that. We can do it very precisely. You can see here we can do it to lots and lots of decimal places. These numbers in brackets at the end here show the uncertainty we have, how much wiggle we think there would be on these last digits given the limitations of the calculation we can do. So this can be predicted to about 1 part in 10 billion by the Standard Model. And then we can go out and measure that number in experiments. We can go and see how does an electron behave. And incredibly, that can also be done to 1 part in 10 billion. And if you look at the uncertainties you have on these numbers, how much wiggle we think there are, these two numbers agree. So within the uncertainties, within the wiggle we think should be there anyway, given the limitations of our experiments and our calculations, these two numbers agree to 1 part in 10 billion. So this is a theory of nature that really describes what we see to phenomenal precision. It's a roaring success. And it's also very coherent. So if you ask how well the various parameters you can measure agree with one another, which is shown by the different coloured regions in this plot, which is as a function of the mass of the top quark and the mass of the W, and these lines overlaid show you the mass of the Higgs. These different coloured regions, they overlap really well. And so you find something that's terribly self-consistent. It makes sense within itself. And I think, given all that together, the theory's beautiful. It's one of the pillars of 20th century science. I think if you asked a particle physicist, they'd claim that it's one of the most amazing things that humankind's ever achieved. It really is an absolutely amazing description of the universe. Unfortunately, it's also a catastrophic failure. So this amazing quantitative theory we've got, it tells us about this kind of 4% of the stuff that we've got in the universe. This 23% of the matter that we think is in the universe, we have no clue what that is. The Standard Model can't tell us anything about what that matter consists of. We do an even worse job in explaining the energy that's out there in the universe. We think there's some 70-odd% of the energy that's in the universe that particle physics just tells us nothing about where it comes from. So one of the few things that all particle physicists would agree with is that we expect to discover new particles, new forces, to explain these and various other shortcomings of our current description. We think those new particles should be rather heavy, otherwise we'd have already seen them in the experiments we've done. So how do we search for these? Professor Davies already alluded to this somewhat. We can use what might be termed brute force. We can take some protons, here they are, inside an experiment. We can smash them together as hard as we possibly can. And then if we zoom in on this region where the collision happens, then we can see the traces they leave in our detector, whether we can spot something new. Some new heavy particle we haven't seen before. We can also try, perhaps, to do something a bit more subtle. And I'm going to surprise my children here a great deal to hear, because they're going to hear that I'm involved in the more subtle version rather than the brute force version. We can take a particle like a B quark, and we can try and understand if the way it falls apart, the properties one gets when it turns into other particles, if that happens according to what the standard model says, so if it agrees with the standard model description, or in addition, we need a contribution from some new particles, some new force or some new particles that we term new physics. Why might we want to look for these new particles in this second way? There's a property of quantum physics that means that the particles that exist for only some fleeting instant in the middle of these kinds of processes that we're talking about, they don't behave like the everyday particles. We can see the influence of intermediate particles that will be much too heavy to be created by the brute force method. So, for example, in this process that turns a B quark into a C quark, in the standard model, that happens via this W from the weak nuclear interaction, and it produces a muon and a neutrino, for example, one of the other particles and its associated neutrino. But there could also be something in here from a very heavy new physics particle, much heavier than we'll be able to create directly by brute force. Similarly, in this process, at the bottom here, this turns a B quark into an S quark, and these particles are muons. There's lots of intermediate particles in here. Again, we could have the influence of something very heavy that we wouldn't be able to produce directly. But because there's lots of intermediate particles in here, this unfortunately makes this process rather rare. It doesn't happen very often. But what that means is that we could see a commensurately smaller new physics contribution and still be able to resolve that over what happens in the standard model case. There's another reason we're interested in studying these particles. If we look, searching for new physics in this way, if we look at the interaction strengths of the quarks with the W I talked about on the previous slide, or indeed if you ask about the interactions of all of the particles with the Higgs, particles that, the particle that gives them mass, then we can really see a clear pattern. So these diagrams on the right, the shading is supposed to tell you how strong the interaction is. So on the top right here, this is for the W, so it talks very strongly to the up and the down, but less to the up and the strain. So you see that the shading is different here. So for both the W at the top and for the interactions of the Higgs in the lower part of the slide, there's a really clear pattern in the strength of those interactions. Now, according to the standard model, that's an accident. These numbers could have been anything, and yet they come out with this extraordinary pattern. And so what we think is that can't be just an accident. That must come from some symmetry that we don't yet know about. And if we can find, if the experiment can give us a clue about what that symmetry is, then maybe we can unlock the physics beyond the standard model. Unfortunately, nature's not quite so kind to us. So, we can compute the properties that we expect for this B to S processes rather easily. So we can compute that precisely. But we don't see single B quarks in our experiment. Instead, we see these B quarks bound together with some lighter quark in a combination we call a B meson. And they're bound together by the strong interaction. So what we're interested in this process, that happens in that dot in here. And we invariably get in all of this strong interaction physics. And if you remember, that strong interaction physics, that's the bit that's difficult for us to predict. That's the bit that's difficult for us to compute in the theory. So what we have to do is to find those special quantities to measure where for one reason or another, the theoretical predictions are really well controlled. then we get something where we can go and make a measurement in an experiment, compare it to the theory, and really understand if what we're seeing is compatible with the standard model description or requires a new physics contribution as well. Okay, so where do we get these beam mesons to study? Well, the world's most intense source of these particles is CERN's Large Hadron Collider. So 100 meters underground, straddling the Swiss-French border just outside of Geneva, is one of the wonders of the world. This is CERN's Large Hadron Collider. It's a 27-kilometer round circular accelerator. We take two bunches of protons, or beams of protons. We accelerate them very nearly to the speed of light, and then we smash them together in these areas where we place experiments. So these particles are going so fast that they can go round this 27-kilometer ring 11,000 times a second. And it's 27 kilometers around. Now, the processes we're interested in are rather rare. And so we want these beams to collide with each other rather often. So we fill the beam with as many protons as we can manage. And we can create in these experiments, we do create in these experiments, 10 million interactions a second. And we have to process, or be able to process, all the data that comes out from that. So just out here, quite close to Geneva Airport, it's a specialist experiment. If you go 100 meters underground, there's a specialist experiment that's designed to study B quarks, and that's called the LHCb experiment, Large Hadron Collider Beauty experiment. I'll say some more about that in a moment, but maybe I can give you a glimpse of what the accelerator looks like. So if you go down into the tunnel, you can see a long kind of tube like this. So we have to empty the space where the beams go from other particles, so to create a vacuum. And in fact, we have to do that rather well. This is the emptiest vacuum in the solar system. So there's something like 10 to 100 times more atmosphere on the moon than there is in this accelerator. Moreover, the magnets that we use to keep the particles going round in that circular trajectory, they have to be cooled down to the temperature of liquid helium. This means that this is the coldest place in the galaxy. We operate this device at minus 271 centigrade, so pretty cold. And then we smash these particles together so hard that effectively we're creating temperatures 1 billion times hotter than those in the sun. So it really is an extraordinary endeavour. And that brings me to the LHCb experiment. So the proton-proton beam come in along this line, and we smash them together in this region on the left, and then the debris of the collision spreads out, as you see indicated by these lines. We have a set of different systems, like a bit like layers of an onion, that measure different properties of the particles as they go through. So this experiment was built, or designed, and is operated by an international collaboration of about 1,200 physicists drawn from institutes worldwide. On this next slide, you can get an idea of what it looks like in situ. So I'm afraid this picture has not come out terribly well, but there's a kind of wedge-like structure in here, and this over here is the magnet that was on the previous slide. This blue item is a large magnet we use to bend the particles, and that tells us about their momentum, and you can just about, I hope, make out that structure in here. So this is about 20 meters across, it's about 10 meters high, and it really fills the space available. There's a person sat cross-legged on top of this platform, which perhaps gives you an idea of the scale of this medium-sized experiment for at least this field. Maybe the picture's a bit clearer if I show you a side view of the experiment. So again, this is the region in which we create the collisions along this line where the beams circulate. Here's that large magnet in here. I'm going to take a moment to say something about this particular detector system in here. This is a detector, well, when I first went to work on this experiment in 2004, I actually worked on this particular detector, and the Imperial College group, I was then working for CERN, but it was the Imperial College group from here who were leading the design of this detector. So what this does is when a charged particle goes through this device, we have a gas in here, and the charged particle, that makes the charged particle give out light. We bounce that light off a series of mirrors. So there's a mirror here and a mirror here. We bounce that light off mirrors into a set of photon detectors either down here or the equivalent happens up here. And the angle that the light comes out at, that depends on the velocity of the particle. And if we've already measured its momentum, then that helps us figure out what kind of particle went through. So we can compute its mass and therefore what kind of particle it was. So this is a device that helps us figure out what kind of particle went through our detector. So I joined the experiment in 2004 and I was asked to help out with this detector. One of the first things I was asked to do was to help out in the lab with these photon detectors that help us detect the light in these planes down here. We'd just received the very first of these very expensive detectors from the production run, so from the company which had been assigned to make lots of these for this experiment. So there were only a handful of these in existence anywhere in the world, and we had to take the first tubes from the production, put them in the lab, test them to see if they were working as we expected. So we took this down to the lab, and it requires, you can just see these cables at the back there, it requires a high voltage, plugged it into the lab setup, turned it on, and then there was this terrible burning smell. And after that, the tube didn't work anymore. So, my CERN bosses decided perhaps I wasn't cut out for this lab work, and that I would be much safer given some tasks to do on software where I could cause less damage. So what they asked me to do is to figure out whether the magnetic shields that we put around these detectors to protect them from the magnetic field from this very large magnet that would otherwise disrupt them, whether those shields would work. Now this is an awful problem. You have to make a finite element calculation where you have this very big magnet, but these rather small photon shields around each of the photon detectors. You need to couple those two elements in the calculation to some extent. And that proved to be terribly difficult, but we eventually managed to solve this with the input of the Imperial College group who were leading the design of this magnetic shield. They really helped us crack this, and we were able to show that those would work. I also, during this time, was able to look at the reconstruction of these events. So once we get this light down here onto this plane of photon detectors, we get lots of hits on the plane, and we have to figure out which of these came from which particle going through our detector. And in fact, they make these kind of ring patterns. So at the time, the performance of this device had really fallen off a cliff compared to the performance that we expected to get. And working in collaboration with a colleague from Cambridge, we're actually able to recover that performance and get back to the kind of design values for which the device had been built. So that's probably still one of the most important things we did for this experiment. And then finally, I mentioned that these detectors produce really vast amounts of data, so colossal amounts. So much so that an individual physicist needs access to a worldwide collection of enormous numbers of computers in order to be able to process the detector to try and make a measurement of something that tells you about the particle physics. So one of the other things we did during this time was really to try and establish that that system was going to work. When this data started pouring in, and I did this with a colleague from CERN who was really responsible for creating some of the elements of that system. He was 6'5", so somewhere up here, and rather more handsome than me. And so we amused ourselves by putting this picture from Monsters, Inc. on our talks. All right, so if I bring us back to the present day, my fantastic colleagues here at Imperial have continued to work on this detector. So we've just put in a completely redesigned version. So the system to hold all the photon detectors, that was designed by the fantastic team we have in the design office. So this was done in this building. Here's a CAD picture that was put together by our team. And even better, our amazing technical team really made this thing in this building. So here it is. They really went from this design to a real object that was built by our incredible tech team here. And in these lower photos, you can see we shipped this thing out to Geneva, and here the guys are installing it in the experiment. So you can just about make out, I hope, the coils here of the magnet that show them putting this in the detector. So one of the things I want to emphasize is that, you know, without these kind of technical contributions, both in the design and in the manufacturing and in the software, we really wouldn't be able to get the science out. We rely on this team and all the fantastic talent of all these different tasks and elements in order to really get out particle physics measurements we're interested in. So this is really a multi-layered and certainly a real team effort. Okay, so let me come and try and say something about what we see in these experiments. The experiment was kind of approved in its final form in 1998, and it took about a decade, it took about a decade for us to really build that experiment. So about 2008, we were basically ready. And then there was something of a false dawn from the accelerator side, so it took until about 2010 for us to really get our first glimpse of data all the way through this experiment. And this was a fantastic time because we were really able to show for the very first time that we could see this process that produced a B, or turned a B into an S and these two muons. So we could really see this process we were interested in measuring for the first time. So this shows you the mass of the particles that come out. So if I take all of these particles and figure out the mass of them, then if they really come from this process, then I should get something that corresponds to the mass of what I started with, in this case, this B0 meson. So what you see here is the number of times, how often we see a particular value of the mass. So here's the value we'd expect for the nominal B0 mass, and you see that we see some accumulation, very little noise or background in this plot. So we're really seeing an accumulation just where we expect it from this process. There's only about 20 events in this process, but this was really the first time that this had been seen in Europe. It had been seen in other experiments before, but this was proof that the whole chain, all of those elements were working. We're really being able to isolate the signature that we were interested in studying. And then things moved rather quickly. So just a year later, our peak looked like this. In the course of a year, when this thing started running, we accumulated the largest sample of these events that the world had ever seen in 1 year. And over the course of the next decade, we've really been running this and making more and more sophisticated measurements. But this first data really allowed us to establish the techniques, all the bits you need to make the measurements. So to isolate the signal you're interested in isolating, to really think about the effects your detector have on the quantities you want to measure, and then to really isolate and make a measurement of the quantities you're interested in measuring. Each of those really required some developments. Using those first data sets, we were able to really measure this process with LHCb for the first time. So this shows you one of the first measurements we were able to make. This shows you the rate, how often we saw this process with producing an S-quark and these muons as a function of what we call Q squared, which is the mass of these muons squared. So it's just a shorthand for the mass of these muons squared. So the blue band in here is the theory predictions as they were when we first made these measurements. They've subsequently improved. And then if I average those theory predictions over the regions in which we make the measurements, then you get these purple bands that you see in here. And then the crosses in here, these are the LHCb measurements. So these were the measurements we made in 2011, 2012. And the height of this band in here, this vertical line, this gives you some idea of how sure we are of our measurement. What's the uncertainty? How much wiggle would there be in that value given the limitations we know about in what we've done? So these vertical bands give you the uncertainties on the measurement. And what we were seeing here was that the rate agrees, at least in these first measurements, rather well with the predictions from the standard model. So this really gave us some confidence. This full chain worked. We were really seeing a rate of these decays as a function of this mass that agreed with what the standard model said we should see, at least with that precision we had early on. Now I need to explain for later why there are these holes in this plot. In here, in addition, if we want to find these particles in our detector, in addition to that being possible by turning a B quark into an S quark and producing these muons, there's another way. We could take a B quark and produce a C bar, and again an S, and this C bar turns into a particle we call the Jape psi, and that Jape psi in turn can fall apart to two muons. So if that happens, we end up with exactly the same particles in the detector that we would expect from the thing we're interested in. okay? But if that's the case, then the muons we get out, they should have the mass of the Jape psi, and that happens in this region. And so we cut out the events in that region so that we are looking only at the process we're interested in and not in this process that we're not interested in. And similarly, there's a heavier version of the Jape psi in here. We cut that region out as well. And then sometimes the theorists don't predict the region in the middle, sometimes they do. And so in this particular plot, there's no theory prediction in this region, even though, as you see from this cross, we're able to make the measurement. Okay. So with this incredibly large data sample we were able to accumulate, we were able to then make much more sophisticated measurements than anyone had ever made previously. And in particular, by measuring the angles of the particles produced, this gave us access to quantities where the effects of that strong interaction, the bits that are difficult to compute, that cancels out to some extent. So you see one of these quantities on the lower part of this side. This shows you the so-called forward-backward asymmetry, AFB, as a function again of this quantity q squared, which again is related to the mass of those two muons. So what's this AFB? Well, it's the number of the muons that go forward minus the number that go backward relative to the B direction. Okay, so we take the angles that we see the muons come out, then we can form this quantity, forward-backward asymmetry, AFB. And the point of measuring that is that you can get different distributions in the standard model and in different new physics models. So if we measure that, we can understand if what we're seeing agrees with the standard model description or not. So I had the great pleasure of working with a fantastic team of young people that really established the method and made the first LHCb angular measurements of this quantity. So there are lots and lots of different plots I could show you. Let's just focus on this lower one, which is exactly this quantity, AFB, again as a function of q squared, the dimuon invariant mass. The purple bands in here are again the theory predictions from the standard model, and the points in here show you our measurements, and with the precision we had in these first measurements, they agree beautifully. So we're seeing something that's really consistent with the standard model description. So much so that when we first presented these results, I think I showed this first at the European Physical Society conference in 2012. This was picked up by the summary speaker from the conference, and they described this as a validation of the standard model that was so beautiful that it should be in textbooks. So we were really thrilled that we were able to measure this to this precision. Okay, during this time we were also able to show that we could look at this process that turned a B quark into a C quark and produces a muon and a neutrino, a tau and a neutrino. So one of my PhD students was able to show that we could do this. Again, you don't see these B quarks in isolation, you see them in some bound state. So in this case, a B with an anti-D quark, and this produces a particle called a D, or there's an excited version of that called a D star. So in this case, you produce one of these very inert particles called a neutrino. These guys don't talk to the other particles, they don't talk to matter. They typically leave the detector without leaving any trace in our experiments. And so in this case, we can't find all the particles that came out from the original particle, and therefore we don't expect to see some accumulation at the mass of just a B0. We expect to see some spectrum. So what my student was able to show was that we could reconstruct that spectrum and separate out the bit of this distribution that comes from a D star and a muon, and separate it from the bit that comes from a D star and a tau. And that's interesting because what you want to do is measure the rate, the ratio of those two, the rates of those two processes, because that's something that you can predict cleanly in the standard model. So this is something that we really didn't dare imagine we could do with this experiment, given that neutrino which we're not able to reconstruct. But thanks to the ingenuity of the PhD students, we really were able to do this. After those kind of first set of angular measurements, I was asked to lead a group that was responsible for looking at all these kinds of rare processes at LHCb. And the key thing we then set out to do was to expand the program from the flagship processes we'd looked at in a kind of first bite to the entire suite of processes that can occur with different light quarks and different final states. And so while we were doing this, we really got our first surprise. So there was progress on the theory side, and that gave us new quantities to measure with better predictions, so better idea what you should see in the standard model. And you see one of these that we were able to measure here. This is a quantity called P5 prime, fancy name, but it's just derived from the angles of the particles you see in the detector. And again, as a function of this quantity Q squared, the points here are the LHCb measurements. The bands are what you expect from the standard model theory as it was back then. And in this region, just below where we cut out the Jape psi, you see there's a whacking great difference between what our experiment measures and what the standard model says we should measure. And in fact, that difference has persisted right to today. So here are the state-of-the-art measurements. We now have so many events that we can measure this in 2 different regions. And in here, you can see that our measurements really don't look like the predictions from the standard model. Actually, I should say that there's a part of our team here are really working on the update of this with about twice as much data, and that's a result we're expecting to produce in the next couple of months. So we're going to get an update of this real soon. Okay, well, if I go back in time, the experiment really succeeded in that broadening of the program. So what we now have is a whole host of these different rate measurements. I showed you one, now we've got loads of them in loads of different final states. So I'm not going to go through all these plots. They all show the rate on the vertical axis as a function of this quantity Q squared, the mass of those 2 muons squared. And all I want you to draw your attention to is in every single one of these plots, with different particles involved, what we see undershoots is below the standard model prediction in every single one of these. So these are all mediated by this B to S process. In all of them, exactly in the same region, we see this difference in the angular quantities, so this P5 prime. We also see a rate that looks low compared to the standard model prediction. We've also made angular measurements in similar processes. So this shows you again this quantity P5 prime as a function of Q squared, but now it's a different one of these B to S processes. And again, in here, you see the measurements lie above the standard model predictions. And this has actually been done by other experiments. So in particular by the CMS experiment, they've done this, and they get values that are bang on top of the LHCb values. Something gone slightly wrong there. I'm sorry, that's gone sideways. We also, these B to C processes have really turned into an entire industry. So you can't see this very well, but what it should show is that we measure lots and lots of different variants of these B to C processes. What we're interested in is the ratio of how often the process that produces the tau occurs versus how often the process with the muons occurs. We can do that as a function, we can do that for both the processes that produce a D on one axis and the processes that produce a D star on the other axis. And what these various contours, if you tilt your head, show there are lots of measurements in here from different experiments. None of them individually looks that incompatible with the standard model prediction. But if you average them, then you get this red contour in here, and that actually really is some distance away from the standard model prediction, which is given by this cross. So here again, in all these different B to C processes, if you average everything, you again see a difference with the standard model predictions. So, if we put all these differences we see together, do they rule out the standard model? Well, in this plot you can see the strength of the new physics interactions you'd need to explain the data. So, if we have new physics interactions that are in this green region, then we can account for all the differences we see in these B to S processes. From the angular distributions, from the rates we observe, we can take care of that all in one go if the new physics has the strength of interactions in this green region, and these lighter shaded regions show you the uncertainties that we have in that. That green region is miles away from the standard model, which should be up here at 0, 0. So no new physics interactions. If we add as well the B to C differences we see, so from those ratio of rates, then we get these values that you see in these red contours here, where again, these show the uncertainty that we have. So once again, this is really some distance away from the 0, 0 value we expect in the standard model. So I think this is the first time we've really seen a coherent set of differences from the standard model predictions, perhaps in certainly working life, or I don't want to quite say living memory. But this is pretty exciting. Could this finally be the much anticipated new physics that we've been searching for? Well, one of the problems of being an experimentalist is that you never really know if everything is done correctly and you've done everything and everything is completely done perfectly, right? There's no textbook you can go and look in to check that you've taken care of all effects. And so you literally wake up in the middle of the night, sit bolt upright and think, oh my God, did we take care of the effect from this? So you never really know. And as a result of this, on the experimental side, what we can do is we can make additional measurements to try and check our understanding. So we make a cross-check here, we try and check a quantity there. We make ancillary measurements to really convince ourselves that we've grasped all effects, we've taken care of everything that matters. But nobody ever rings a bell when you're done. And as a result of that, the community are, quite rightly, very sceptical. The community in general would like to see multiple effects that really triangulate and tell you this can only be a new physics explanation. There's no other possible way out here. And they want to see that from multiple experiments, from multiple different data sources, before they'll really believe it. And I think that, that's a barrier for proof that we haven't quite met yet. But on the theory side, one of the things that the theory community can do is they can ask the question, well, is this even possible to explain with a new physics model? And the answer to that question turns out to be yes. If in nature particles such as these, so-called Z prime or a so-called leptoquark existed, if those particles were something that really happened in nature, then these could take account of what we're seeing. They would be able to explain the data. Why might we expect these kinds of particles? Well, that takes us back to these different families that we were talking about. If you try and extend the symmetries of the standard model in a way that connects the upper part of these pictures and the lower part, and remember we see the same number of families in each case and they each get heavier, then you necessarily get particles in particular like these so-called leptoquarks. So these come out of these kinds of theories where you try and extend the symmetries in this way. Now, these have been known about since the 1970s, but they actually fell out of fashion because one of the things they predict is that protons should be unstable. But when we look, we find that protons are really very, very stable indeed. So what the theory community now have happened upon again, given the data that we've measured, is perhaps these leptoquarks, if they exist, they could be like the Higgs boson. They could talk more to the third family of particles than to the second family, to the first family, and therefore you'd get the weakest interactions with protons, which are composed of the first family of particles. So maybe there's again that pattern, and that could explain this data. Okay, so before we get too excited, we better check again that there isn't some standard model explanation for what's going in here. So the community have looked really carefully at all the different aspects of the predictions. And one thing that some people worry about is whether there could be a residual effect from these CC bar processes that I talked to you about. So, in addition to the JAPE psi and its heavier version, these potentially can come in other places. Could they be leaking into this region in here and causing us to see the difference that we see both in the angular distributions and in the rates? And I think it's fair to say that that's caused a lot of, in some cases, quite heated debate. With the checks it's been possible to do so far, it doesn't seem to be the case that this is a standard model effect. What we're seeing is that the calculations that are done seem to be robust, but not everyone is convinced by that. I think that's a fair thing to say. So how can we get out of this situation? Well, one thing we could do is to measure a quantity where everybody agrees that the prediction is completely pristine. There's no possible way out. And one such quantity is the ratio between the rates of these B to S processes, where you compare the electron process to its muon equivalent. So if you make a ratio like this, then this is something that everybody agrees, pristine. Can't make a mistake here with the predictions in the standard model. The prediction for this is really very close to 1, and there's no way to get around that. So if new physics talked to the muons differently than it talks to the electrons, if that were really the case, then maybe one could see an effect here, and maybe that would be a way forward. And the story of this series of measurements has so many twists and turns, it could be a soap opera. And I will cut a very long story short by telling you that, a series of measurements got us properly excited. We really thought we had it. But in the end, when the final calculations came in, this quantity went back to being consistent with the standard model predictions. So if these if these effects we see in the rate and in the angular distributions are from new physics, then it's new physics that talks the same to the electrons and the muons, at least within the precision of these kinds of measurements. So where does that leave us? Well, the latest analyses try and use the data itself to pin down any potential residual effect from these CC bar processes that people are worried about. So you see in this plot, this shows you this quantity again, this angular quantity P5 prime as a function of Q squared, but in here you see there's no holes. We've really tried to fold in the effects from things like the Jape psi and other equivalent guys. And what happens in that analysis is you see something again that doesn't look like the standard model prediction, given the effects that are folded in. There's another approach in this lower plot that shows you P5 prime as a function of Q squared, and here we've tried to separate out how much shift in P5 prime do these CC bar effects cause? And the answer in this plot is not much. So again, potentially new physics-like. But we know these don't cover every single effect. So unfortunately, we're still in the position where, for most of the community, the jury is still out on exactly what it is we're seeing here. All right, so let me come to my final section. How might we get some clarity going forward? Well, further measurements of these B to S mu processes will really help us improve our understanding and nail down whether we really are encompassing all the dynamics that occur here. So we're really able to show that all the effects that should be there are there, and we agree with what's going on. So more precise measurements, I think, will really help us here check and improve these kinds of measurements and hopefully help us pin down what's happening. Other experiments could help here. So if instead of the process that produces muons, we instead look at the process that produces neutrinos from the same kind of process, then the CC bar contamination, it doesn't affect these nearly so much. This has been measured by, in several different ways. You see the measurements here. If you average all those measurements, you get this blue band. So this isn't from LHCb, it's from other experiments. So this blue band is what the experiments give, and the standard model prediction is this brown band in here. So you see at the moment, these measurements are a little bit above the standard model prediction. And if this were to persist, I think it would really transform the picture that we have here. But this is a really very difficult measurement, and there's not yet clarity from that. What about these B to C? My plot here is a sideways again. What you should be able to see in this is that all these different measurements, none of them individually looks like it's in that much tension with the standard model. It's only when you average them all that you get something that doesn't look very standard model-like. And what that means is we have to do the hard work of improving all of those measurements. So we need to shrink all of the uncertainties from all of those measurements. And they're very difficult measurements. They're rather time-consuming. And it's difficult to assure oneself that everything is done correctly. So I think this story here could run and run. And then, if this data really is explained by new physics, then one of the things you might expect is the rate, instead of a B turning into an S and muons, if we take the heavier version, the tau, so now B to S tau tau, if there is a new physics contribution, then the rate of these processes could be massively enhanced. by factors 10 to 1,000, even 10,000. So one could see an enhancement here, a higher rate than you predict in the standard model, that's so much bigger than the standard model prediction. I think it really could be a knockout blow on the standard model. In this plot on the right, you see the rate for these B to S tau tau processes are a function of what we see in the B to C data. So if we want to take care of the B to C differences that we observe, we have to be in this dark green region. And then these coloured bands show you as a function of that the predictions for various processes that are underpinned by this B to S tau tau process. So up until now, experiments have probed this rate down to this line here, so ruling out this grey region. Over the next set of measurements that we hope to be able to make over the coming years, we hope to get down to here. So we'll really be able to probe the region that can explain the B to C difference that we see. But we don't know whether the rate really will be enhanced to that extent. So what if that doesn't work? What if this new physics, what if there is a new physics contribution rather than the standard model explanation, and it persists only in appearing in these muon processes? Then one of the few options we'd have is to try and run this process backwards. So if we tried to collide muons and produce quarks in something like a muon collider, then we'd expect to see some kind of anomalous effect. Now the problem here is that the new physics could be so heavy, the new physics you need to explain the differences we're currently seeing, it could be so heavy that it would be really beyond the reach of the next generation colliders that are envisaged at CERN, and that resulted in my favourite headline about this work, anomalous bottoms at CERN and the case for a new collider. Now, what if all of that doesn't work out? Well, I told you earlier that we expect new particles, new forces, and that we think that they should be rather heavy. But what if rather than being heavy, these new particles have comparable masses to the standard model particles? It's just that they interact much more feebly. So they're very, very feeble interactions. So this was an idea that one of my LHCb colleagues convinced us, a small team of us, that we should take seriously. And way back in 2013, he got us together to propose a new experiment, the Search for Hidden Particles experiment, SHIP. You see a schematic of the layout that's proposed for this experiment here, to try and search for these very feebly interacting particles. And last March, CERN actually selected that experiment as something that the lab's going to do. So we're working hard on the design with the hope of taking data with a new experiment from the mid-2030s. Okay, so let me wrap up. The paradox of the standard model convinces us that we think there's more new particles, new forces out there for us to discover. The latest LHCb results give us tantalizing hints that potentially we're seeing something new, but it's hard to be definitive, and therefore we're looking forward to a next decade of measurements going forward. Let me make one last word. It's been a real privilege to be allowed to spend this time trying to understand why we have these different families of particles and being allowed to do this work, which is really interesting. But I could not have done so without the support of my family, my kids, Lila and Mira, and my long-suffering wife, who has lost many evenings and weekends to this work. So I'd like to thank my family. To the LHCb team here, both past and present, your talents have kept the group here at the forefront of these activities for more than a decade, and it's been an absolute pleasure to be a part of your journey, and so I'm tremendously grateful to have had such fantastic colleagues to work with. To my close family in the particle physics group here, this is really a really special place to work. I have colleagues here in the group who have never worked with me directly on an experiment, but haven't hesitated for a second to help me out with whatever support I needed, and have done so without hope of return on their investment. So this is a place where people really get together, and as a result, the group behaves as more than a sum of its parts. And so it's a real delight to be in that environment. And the same applies to my wider colleagues on the teaching side and elsewhere in this fantastic department. So it's really been a privilege to be here in such a fantastic place and to do this work that's so interesting. Thank you very much for your attention.
Let me say on behalf of the audience, thank you, Mitesh, that was fantastic. We have some time for questions. Anybody questions in the room first? We have a couple of mics, so if people could just wait. Anything from the room? Stunned silence. No?
Oh dear.
We got a question in the middle, Matt.
So you're possibly searching for heavier particles. So how confident are we that there's only 3 generations of fermions?
So we're really quite confident. We can measure how that particle, the Z, falls apart, and we can do so, and it gives us a constraint on how many generations of particles there are, less than half the mass of the Z. And so we know very conclusively the answer is 3. One can search for additional quarks directly, and there are very good limits on whether there could be a heavier generation of quarks as well. And so from both those measurements, I think people are pretty convinced that there are only 3 generations. But, you know, in this field, one should never say never.
Ooh. Right. Oh.
Yeah.
Now you're under pressure. Don't mess this one up. Don't mess this one up.
This is my youngest daughter.
This is a star of some of the pictures, I think, so we carry on.
Come on, you have to go ahead now.
What are you proudest of?
Well, my proudest of... Oh, that's easy, you. And Lila.
Hey.
So, if you want to ask me the question with respect to work, I think the thing I'm proudest of is the people. So we've had really incredible teams here. People who I hope will be, you know, lifelong friends who have really gone out, done work here and then gone out. Some of them are here, some of them have gone to other places. But seeing those people, you know, really achieve their potential has been a great privilege.
Just before we come to the back, Scott, have we got people questions online?
Yeah, we have a question from a Year 12 student, Aditya. He asks, how do quantum loop contributions affect precision measurements of standard model parameters, such as the muon G minus 2 or the Higgs boson mass?
Give me that again. A bit more slowly.
How do quantum loop contributions affect precision measurements of standard model parameters, such as the muon G minus 2 or the Higgs boson mass?
Right. So, can I go back? I'm not sure if it's wise to go back. Anne, is it wise for me to go back? Is it okay? So if I go back to this slide about, it's right near the start. So the answer to the question is kind of like this. So these are loop corrections to the standard model prediction for, in this case, the anomalous magnetic moment. And so you have to compute these kinds of complicated processes, and those affect the standard model prediction for the quantity. So this is only done to some particular level of complexity of the processes. And that gets more and more sophisticated. And each extra layer of complication you add, there are more and more processes that you have to take into account, compute. It takes a long time, but in the kind of theory that you need to do these calculations, you can add as many of them as you like. The Higgs is a different prospect. The Higgs creates a problem that we really don't understand. So when you try and do the loop corrections for the Higgs, what should happen is that loop that you have to add, the corrections from it, those should come from the heaviest particle in the theory. And what that should do is make the Higgs blow up and give you a very high value for the mass. So something has to cancel that contribution, and we don't really understand the mechanism for that calculation because it appears to need to be very, very precise to a degree where people feel that the solution to that is unnatural. and that they feel that there should be additional contributions from new physics particles that help us explain why we get relatively low value for the standard model Higgs mass.
Okay, thanks.
There's
There's a question at the back. Yeah, sorry.
So, ladies and gentlemen, this is my PhD supervisor. So I'm slightly frightened
The
about
one
this
you
question.
didn't answer in the Viva. Here we go. Yeah.
I just wondered what you're really hoping for from the current upgrade at LHC.
So, yeah. So we ran the upgrade last year for a year, and we got a data set that was the same size as we'd managed in the previous 10 years. So for each year of data taking we're now able to go forward, we'll get a quantity of data that's like everything I've shown you in a year. So we've made that leap up in precision. There are plans afoot to go further. Already on the drawing board are the upgrade after the one we've just installed, where we're hoping to go even, it's not quite an order of magnitude, it's about a factor 5 higher still, and try and accumulate data even more quickly to make even higher precision measurements. So I think that, you know, we've made one leap and we're starting to think about the next.
Okay, any other questions in the room? Hannah, one behind you. Yeah.
It was said that you enjoy education.
I enjoy education. I'm not sure my students enjoy being educated by me, but...
I enjoy educating people too, and I enjoy being educated. How important is it for you to see how many people understand what is happening in the area you are researching? And how important is it for the science to have an educated, very broad background? In my childhood, we were going on to a break and we were talking nuclear physics, Hilbert spaces, Banach spaces, progress in quantifying symmetries, this 10,000 pages paper, yeah?
So, I mean, there's a couple of things to unpack there. There's a kind of difference between giving people a glimpse of some of the things that go on and them really understanding them to a degree where they're able to make the connections themselves. And I think, you know, it's a funny thing about university education in particular, where you can try and inspire people to be interested in the subject, but if they really want to grasp it, there's no quick fix. You have to do the work. You have to make those connections and do the math often yourself in order to really be able to understand, that's why it works. And there's no kind of short circuit to that. So, you know, often we find ourselves trying to inspire people to do the graft, to do the hard work on their own to build their understanding, rather than being in a position by giving a talk to create understanding. I can tell you all the right words, but that doesn't necessarily mean they go into your head and connect with all the other bits of physics you may or may not know in a way that then allows you to make the next step. And I think that there's always a kind of individual aspect to that latter part. And that's something I remember as a student myself struggling with. You go from school where they tell you the stuff and that's enough. You can pass the exam just by being told the stuff. But now at university we ask you to understand the stuff, and that requires you to do a degree of work on your own that is really effort. But you know, even as a professional scientist, you still get to the point where you sit down and you're like, do I really have to think about this again? It's hard work. Yeah? So you have to keep motivating yourself to do that hard work. And a big part, in my humble opinion, of university education is inspiring people to want to do it. I better stop talking there.
It's a very good point to stop. Very good. Anything? We've got one more question at the back. Let's make that the last one, maybe.
How important is reaching a balance between finding the properties and qualities of existing particles predicted by the standard model and discovering new things?
So I think that depends a bit on who you ask. There's not a straight answer to that question. So I think both have merit, and the field has advanced through both approaches at different points in its history. So when you don't have the capacity to make a jump up in energy or rate, then of course it's interesting to go and try and measure something precisely so you can understand if what you're seeing really agrees with the standard model predictions or not. But I think it's a bit of a function of time and availability of data and what's happening. And so at different points in history, I think you'd have got your Nobel Prize doing different approaches for depending on what point in history you were. So yeah, there's not a straight answer, I'm afraid.
Okay, let's take the question online then. Yeah, thanks, Scott.
Yep. So from another year 12 student, given the recent anomalies observed in beauty quark decays at LHCb, what do you think is the most promising theoretical explanation beyond the standard model? Are there any extensions like leptoquarks or new gauge bosons that you find particularly compelling?
So I think this leptoquark idea is really nice. Yeah, these were predicted in the 1970s, and they, were obviously shown not to exist. And now the ideas come back with a kind of hierarchical structure. If you try and extend the symmetry group of the standard model, these are one of the things that naturally comes out. So it would be fantastic if such things existed in nature. We don't know if they do. I don't think they entirely make sense on their own. I'm not expert enough to understand the mass mechanism for those guys if they were to exist. And so I think that, it's not obvious whether you need leptoquarks and a bunch of other stuff. I imagine the answer is yes, that one needs, in addition, other particles in order to make really a consistent theory.
Okay, thanks. Obviously see from the questions the enthusiasm and the interest you've generated, but we should move on. So now we would normally have Professor Christina Lazzaroni from the University of Birmingham give the vote of thanks, but she can't be with us today, but she has recorded a message. So if we could just turn to that now, please. Thanks. Thank you.
It's not easy to find guidance on what should be included in a vote of thanks at an inaugural lecture. My interpretation is that the main objectives are to thank all the people who, in one way or another, contributed to making the event possible, to be at least a little entertaining, not to go on for too long so that people attending can escape quickly to the reception that follows and have a chance to talk with the amazing professor being celebrated. I'll do my best to achieve all of this. I'd like to start by thanking Professor Mitesh Patel for the brilliant inaugural lecture that is given today. I'd also like to thank everyone who's attended in person or online and the many people involved in the event organization. Thank you all. I'd like next to say something about how Mitesh has touched my own work and life, and then to express appreciation for the family members who have guided and supported Mitesh on his way to becoming the wonderful individual that we have with us today. Finally, I'll pass on words of appreciation from a few of the many former PhD students, colleagues and friends who's benefited and continue to benefit from knowing Mitesh. I first met Mitesh when I was a research associate at the University of Cambridge, working on the CERN experiment Na48. Mitesh joined us as PhD student from 2000 to 2003, and we collaborated closely on the analysis of Na48 data. Sharing a passion for super lively physics discussions, we rapidly became friends. We measured together what was then the rarest observed kaon decay. We used a new technique known as blind analysis. This involves not looking at key parts of the data until being confident that all possible noise contributions have been understood. There is only one chance to get it right. Once you've looked, you can't unlook. This made it a super nerve-wracking experience for Mitesh and me, but with an happy conclusion. The decay probability that we measured was about a factor 20 lower than the probability of winning the jackpot with a single ticket in the UK National Lottery. David Mundy, Mitash's PhD supervisor, is pictured here with Mitesh and me and colleagues from NA48 during a visit to the experiment of the Institute of Physics chief executive. Here with Richard Batley, member of the NA48 Cambridge group, at the excursion in Lucca during the collaboration meeting in Pisa. Since Mitesh completed his PhD, I've continued to meet up with Mitesh on a regular basis, both for work and for family events. We invariably end up having lengthy physics discussions, which I always welcome and which give him much to think about. Mitesh's parents gave him an early gift and an enormous drive from the belief that as a son of an immigrant and as a Patel, he could and must be exceptional. After physics, Mitesh's great passion is food and drink, as something to be savoured and where new experiences are always to be thought. This, I'm sure, originates from his childhood. Mitesh kindly gave me a family recipe for making curry from scratch, including the memorable recommendation, 10 chilies, more to taste. For someone not accustomed to spicy food, already the minimum 10 chili came as a burning surprise. After adjusting for that, the results was delicious, and the recipe is one that I continue to use. While a PhD student, Mitesh met Kate, who was to be, in the words of Edward Monckton, his lovely other dinosaur. Their wedding was celebrated in a joyous occasion in the gorgeous garden of Kate's parents. Kate tells me that their marriage certificate was filled in by a trainee registrar who for Mitesh wrote status, physicist, occupation, single. I leave you to decide whether the register has special insight. Before saying more about Kate, I want to mention Marcus, his long-term friends from uni. At Mitesh and Kate's wedding, Marcus performed a riff on food, which gives us some idea of how he and Mitesh came to become friends. Legend tells us how Marcus and Mitesh, together with another friend, had a go at combining physics and food, liberating some dry ice from the university laboratory to make ice cream. Dry ice has a temperature quite a bit lower than a domestic freezer, and they ended up with a frozen rock. Here we see Mitesh and Marcus. They have eaten one of Marcus' bread and butter puddings. Once again, never knowingly underfed. There is so much for which we need to thank Mitesh's wife, Kate, and their two incredible daughters, Leela and Mira. Without them, Mitesh would be a different person. They challenge him with new ideas. They involve him in wide-ranging activities which encourage thinking in different ways. They keep him bounded and caring. They allow him the four-dimensional space needed to be an exceptional physicist. Even when you're very young, Leela and Mira came along to science events where Mitesh and colleagues were passionately engaging with a broad public. Many of the people who were supervised by Mitesh as PhD students and or who worked with him as colleagues have sent me words of appreciation to pass on. One thing that come up a number of times is the concept of being Miteshed. A term along this line has been added to the Urban Dictionary, but a former PhD student provided a helpful explanation. When a student shows Mitesh a plot, that plot made him want to see 2 or 3 plot extra. But then the 2 new plots each warrant 2 to 3 further plots. Students make quadratic number of plots as a function of the number of meetings. Students and researchers learn quickly that showing a plot to Mitesh will create more work, but also create better work. They also learn quickly that Mitesh will ensure that they have all the support needed to complete this work. Former PhD students and colleagues with whom he's worked invariably come to count Mitesh as a valued friend. I now want to read extracts for some of the testimonials. I apologise that for reason of time, I don't include all, and those I do include have been edited for length. I hope that I still give some idea of the amount of appreciation and gratitude of so many people who have been on a physics adventure with Mitesh. This is from Sophie Baker, a former PhD student. I remember my time working towards my PhD in the team with Mitesh with great fondness. He is someone who has absolutely infectious enthusiasm for things, namely new physics, good wine, and Krispy Kreme donuts. Mitesh was an exceptional, supportive, open, and honest mentor. This is from Felix Kress, a former PhD student. Mitesh is not only an incredible researcher, but also communicates and presents discoveries in a way the few can. As a supervisor, he struck the perfect balance of motivating me to pursue my work and giving me the freedom to do it at my own pace. This is from Ulrich Egede, head of the LHCb group when Mitesh started at Imperial College. Working with Mitesh at Imperial over a decade or so was a great privilege. When I first moved to Monash, I realised quickly that one of the things I was missing was the ability to sit with Mitesh on a random morning and have a long discussion about some random physics idea that we thought would change the world. This is from Paul Alvarez, a former research associate in Mitesh Group. During my time at IC, it was striking how much Mitesh cares in the best possible sense of the word. That unwavering passion for what he does makes him a great person to work with. Finally, this is from Kostas Petridis, a former research associate in Mitesh Group. Mitesh has numerous excellent qualities, but two particular aspects set him apart from almost everyone I've came across. The first one is his dogged pursuit of physics excellence that permeates every aspect of his work, his determination to break new ground, opening up new avenues. The second quality is his ability to bring out the best in everyone who works with him. Always supportive, eager to help take you the next step. Everyone who has worked with Mitesh loves Mitesh. He brings the group together and he does love a cheeky cocktail or two. I fear that I've gone on for too long, but I hope that I provided at least a little entertainment and that you might have learned something new about someone who is a remarkable human being and professor. I personally wish to thank Mitesh for all the good time spent discussing about physics, about how to save the world in so many ways, and for being a truly caring friend. I ask you to join me in thanking the people who've helped organise today's event, everyone who's attended, the family, friends, colleagues, and former PhD students who contributed to making Mitesh the person that he is, and above all, Mitesh himself.
Fantastic. So I cannot top those words. Only to say it's fantastic to see some of the people whose words were read out in the audience. So please, thank you all for coming. Thank you those online. Can I invite everybody? There's a reception outside. So please come, let's think of the good memories, the cocktails. I don't know if you've got cocktails. And the donuts. But anyway, please enjoy. Thank you very much. Thank you again. Thank you, Mitesh. Yeah, sure.